Hi, I'm Weifang Sun. Today I would like to introduce our work on investigating the conservative property of score-based generative models. Let's start from the training and sampling process of score-based models. We choose to train the score-based models, or SBMs, with denoising score matching due to its lower computational cost compared to other score matching methods. Score-based models have a connection to diffusion models when modeling time-inhomogeneous score functions. In such a case, the sampling process corresponds to a stochastic differential equation, which can be integrated or discretized with an ODE solver or a predictor-corrector sampler, etc. There are two types of score-based models. The first type, constrained SBMs or CSBMs, models the energy function with an encoder architecture that outputs a scalar-valued energy of a given input. The corresponding score function is the gradient of the energy with respect to the input, which can be computed by automatic differentiation. The second type, unconstrained SBMs or USBMs, model the score function directly with a unit architecture. When comparing CSBMs with USBMs, we can prove that CSBMs are guaranteed to output a conservative vector field. However, as mentioned previously, the first half of its model is constrained to output a scalar-valued energy, and the second half is determined by automatic differentiation. Such constraints limit the choices of model architecture design. On the other hand, many state-of-the-art generative models prefer using USBMs due to its architectural flexibility. Unfortunately, the output vector fields of USBMs are non-conservative in general. Here we provide a special case to demonstrate how non-conservativeness might negatively impact sampling efficiency. The first row are conservative vector fields, and the second row are non-conservative vector fields. We can see that under the same score matching error, non-conservative vector fields may require more sampling steps to converge when compared to conservative vector fields. Aiming to preserve both the conservativeness of CSBMs and the architectural flexibility of USBMs, we propose quasi-conservative score-based models, or QCSBMs, which enhance the conservativeness of USBMs through a regularization loss. To quantify the non-conservativeness of SBMs, we define two metrics based on the fact that a vector field is conservative if and only if its rotation density is zero. The asymmetry metric quantifies the non-conservativeness based on the non-zero rotation density. We can further normalize the asymmetry metric to ensure the metric value is in the range 0,1. The asymmetry metric can be minimized through an additional regularization loss. Unfortunately, the asymmetry metric is intractable under high-dimensional context. To approximate the asymmetry metric, we first reformulate it using trace operators, then use Hutchinson's trace estimator to approximate it, resulting in a tractable regularization loss. Implementing the regularization loss requires manipulation of the computational graph. In particular, the stop gradient operator here is required to ensure the Jacobian here be computed correctly with automatic differentiation. During backpropagation, the gradients should be added back manually to calculate the correct gradients. This table shows that our method achieves improved performance under the same number of function evaluations. The figure as right here shows that QCSBMs are indeed more conservative, as measured by the asymmetric metrics across different time steps during the sampling process. Finally, let's take a look at a simple one-layered autoencoder example. A one-layered autoencoder is conservative if and only if W times R transpose equals to R times W transpose. Previous works enforce conservativeness by simply setting W equals to R. We show that QCSBMs are indeed more flexible, since it can ensure conservativeness while not requiring W and R to be equivalent. To sum up, this paper has three main contributions. We first define metrics to quantify the non-conservativeness of an SBM. Second, we enable minimizing the non-conservativeness through approximation based on Hutchinson's trace estimator. And finally, we demonstrate the advantages of minimizing the non-conservativeness by conducting several experiments. Thanks for having me. If you want to look further into this paper, please scan the QR code below for the full paper and the source code.